Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning. And we are at topic number 2, which is machine learning. And that topic is further subdivided into three subtopics, that is 2A, 2B, and 2C. Of course, we are at topic number 2B, which is kind of a medium difficulty level for machine learning. And as before, this video lecture is developed using the personalized learning management system, which is available at www.easymcq.com/goget. The personalized learning management system is accessible using the URL, which is given in green color on the screen. Now, how to make use of this learning management system, that is shown in 6 videos, which are given in a URL in blue color on the screen. So there are many wonderful features in this personalized learning management system which are not there in some of the more popular learning management systems, major learning management systems. So this is all possible because of the feedback which has been given by users like you and incorporated into this personal learning management system. So one of the biggest features and useful features is full text in the content available in the learning management system. So you can type in keywords, short, long, advanced, ensuring the order, and so on, and get all the contents which is relevant, which is color coded, and it's available to you. And then, of course, some people may have visual disabilities. So that is not catered in many advanced and major learning management system. So in this easymcq.com, the students or the users have the facility and the ability to change the font type, the font color, the line spacing, and so on, to make it more readable, to make it more interactive and more useful, right? And of course, you can also track your progress. For example, which topics you have covered, which subtopics you have covered, and so on. That is there. And of course, you can evaluate your learning and knowledge accumulation through online exams. You can do multiple of exams, and their aggregate scores are recorded and stored. You can access them, and it also identifies the weaknesses. And of course, the data and the content is presented in a hierarchy which saves the space and so on. So I would urge you to look at those videos. So there are two basically learning approaches. One is the traditional learning approach, which is slides based and which has its own limitations. And then is the Q&A, question and answer based learning approach, which is proactive, which is engaging, which is very adaptable, and which is very thought provoking also. And of course, the traditional approach has a lot of details. So the approach which has been followed is a blended approach or blended learning, that is making the best use of the both approaches. So this is the topic which we are covering, and the topic is machine learning. And this topic is further divided into 15 questions and answers. And these 15 questions and answers are basically concepts. So concepts which are of kind of a medium difficulty level are covered in this video, that is 2B. So we are at the video 2A of deep and reinforcement learning, and the subtopic is machine learning. So we start with the first concept, that what are the fundamental types of machine learning, and briefly describe them. I will also show you certain pictures also or diagrams to clarify the concept. So those some of them are standard or more frequently used or established machine learning techniques, and the most widely used is basically supervised learning. So what is supervised learning? So we have a model, okay, because it's machine learning, and that model is trained on already annotated or labeled data set, right? And there's a pair. What is that pair? The pair is that this is the data element and this is its class, and that is correct one, right? So what happens is that the model learns to map the input to the output, okay? And of course, we discussed before that we evaluate that model based upon its accuracy for those labeled data, or for those that data which it has not seen before. So that's fairly simple to speak with, to explain. And of course, the common tasks are classification and regression. Okay, so I've been talking about supervised learning. All right. So then is the unsupervised learning, which is also called as clustering. So what happens in unsupervised learning is that the data has no labels, right? And what is the goal? So the goal is to discover, which is called as the knowledge discovery in databases also, hidden patterns or hidden structures or groupings in the data. And those hidden patterns and groupings should be non-trivial and beneficial also. So there are different techniques like clustering, and there are different types of clustering. And then there are dimensionality reduction techniques, which are usually used to analyze the data, interpret large volumes of data. Okay. And remember that the data sets are unlabeled. In unsupervised learning, data sets are not labeled. Then is the semi-supervised learning, which is a best of both worlds, supervised and unsupervised. So it uses a small amount of labeled data, and of course, there's a large pool of unlabeled data, which is the case for unsupervised learning. And it is the best of both worlds. It combines the benefits of both. Okay. And there is the reinforcement learning, which we have covered very briefly earlier. So the agent learns to make decisions by interacting with the environment, and those interactions results in a penalty or a reward also. And then it maximizes the cumulative reward. All right. So this is a new one, self-supervised learning. So this type of learning creates pseudo labels from unlabeled data. Okay. And uses pretext tasks. And so what's the result? The model learns useful representations without the human annotation. So human is out of the loop. So it kind of bridges the gap between supervised and unsupervised learning. And of course, it has been found to be very influential and very useful for computer vision applications and natural language processing applications. Then is the multitask learning. So we have a single model, and that model is going to perform multiple related tasks. Multiple related, not unrelated, related tasks. Multiple related tasks, okay, and multiple related tasks to improve the generalization. So how it shares the representations. So it kind of capitalizes on the similarity to boost the performance and the efficiency, and oftentimes it results in uh, better outcomes. Okay, then as compared to training on separate models. So one model, one for all. And then finally is the multimodal learning. Multimodal learning is integrates information from different data types, for example, text and image and audio, into a unified model. So, what is the benefit? It helps the model to understand complex scenarios more holistically. Therefore, it is crucial uh, in the tasks where we have like visual questions or answering or video captioning and so on. So, in that kind of environment, it is more useful. So, the details are here. So, this is the picture which I was referring to. So, we have the unsupervised learning, and colors are different. And then we have supervised. So, we have unsupervised learning, and we can see that the clusters have been identified. Of course, there are errors also. So this is unsupervised learning. There is no prior labeled data. Now this is supervised learning, so it divides the data set into like a binary approach. All right, and this is semi-supervised learning. So most of the data is unlabeled, but some of the data is labeled. So it seems that it had two types of labeled data. So it has kind of divided into two classes, so to say, right? Because we can see and then we have reinforcement learning. We have the agent, we have the reward points, and moving from one state to another state and so on. So these are the standard and more popular types of machine learning. Now there's a fundamental issue with machine learning is that how good it is at classifying or identifying the unseen data, right? Unseen and unlabeled data. So that is generalization. So in generalization, what we are looking at the training versus the testing performance. So we have two things, overfitting and underfitting. I will talk about it. So, and then we have the Bayes variance trade-off. So I told you variance is how the amount of spread with reference to the average value. And then is regularization, on which we have a whole topic. complexity of the model, the representation of the relationship, size and quality of the training data. So how the volume and the quality basically we're looking at. So if you look at the training versus the testing performance, right? So what we are looking at is comparing model performance on training data for which the class labels were known versus unseen test data. So for example, if there is a model that performs good or well on the training data, right? The data which it has the label, but it purely on test data, it means that the generalization is not good. So that points to a mismatch between the patterns learned and the patterns which were available and which were truly representative of the overall data distribution. That's the point. So there are two things. One is overfitting and one is the underfitting. So overfitting is that the model kind of learns the noise and all the specific details, okay, too well, and that results in poor performance on new data. So for example, I gave you the example of a baby, and that baby saw the mother going to a wedding and by putting on makeup. Now, if the baby is unable to recognize the mother without makeup, that is that and it can only recognize the mother with makeup, that is overfitting. I hope it makes sense. And it captures irrelevant patterns and lacks the generality. Irrelevant patterns is the makeup which was put on, the color of the lipstick and the color of the eyeshadow and whatever. And so it is not good for real world predictions or deployment. So only when the mother has the makeup, the baby will recognize the mother, which doesn't make sense a lot. Then is underfitting. Underfitting when the model is too simple to capture the underlying patterns in the data. So therefore, it's going to perform poorly on training and test data. It will not learn, fail the learning process, and because the insufficient model complexity and inadequate training. So, for example, we are looking at non-linear relationships, right? And we're using a linear model. So that linear model is going to miss the non-linearity. So that will result into underfitting. All right. Like for example, I showed you the example before when we're looking at quadratic discriminant function and linear discriminant function, and we saw that the quadratic functions could separate the two classes better as compared to linear ones. So this is what we are looking at. Then the bias variance trade-off. So these are two sources of errors. So we need to like have a trade-off between them. So what we are looking at is we will be looking at bias for simplifying assumptions and variance from sensitivity to training data fluctuation. So these are two looking at. So for optimal generalization, we need to minimize the both, the bias and the variance. Why? Because if the bias is high, that will result in underfitting, and if the variance is high, that results in overfitting. So we neither want overfitting nor we want underfitting. So these are the two things we need to be taken care of. So why do we have the bias? Because of oversimplistic assumptions in the learning algorithm. So if the bias is high, the complexity in the data are not captured. Okay. So that will result into linear models, which we have just discussed. And variance is the model's sensitivity to small changes in training data. Now, if the variance is high, it means that it is capturing noise rather than the structure, and of course, leading to overfitting. So small changes result in a high impact. Okay. So if the mother puts on a different color lipstick, the next time the baby won't recognize because the color of the lipstick has changed. So what is the result? It results in unnecessarily complex models, okay, which have too much flexibility. So what is regularization? We have a whole topic on regularization. So what regularization does, it kind of penalizes the model complexity so as to reduce overfitting. So how that is achieved, we will cover this. It adds the L1 and the L2 penalties. So what they do is they help improve the generalization. And how it is improved? By the model captures the essential patterns rather than memorizing the training set. Memorizing means that there is low or no generalization. That is memorizing. It's just matching, like working with a database. High, very nice, perfect memory. So complexity of the model, of course, the model complexity affects the generalization. Simple models will underfit and complex models will overfit. I'll show you some pictures, diagrams also. So we need to select the right complexity, okay? And sometimes need to make trade-offs also. So we are here, over here. I'm sorry about that. We are over here. So I'm sorry again. We are actually at the complexity of the model. I got carried away. So size and quality of the training data, that also has an impact, right? Uh, Usually, if you have more data and it's of higher quality, right, that will generally improve generalization. Why? Because there are diverse examples, and the opposite is true for noisy data sets, which increase the risk of overfitting. And of course, the model's ability to capture uh, useful patterns is reduced. So let's take a look at some of the diagrams. So, all right. So this is overfitting. So even say for example the noise, this could be noise as a matter of fact. So even the noise gets selected. So we have this cluster consisting of crosses, and this cluster consisting of zeros or circles. So this is overfitting. All the details, unnecessary ones, are also taken into consideration. This is underfitting. It's too simple, and you can see that this is kind of quadratic relationship over here, but it uses linear fitting. So that is underfitting. This is fine. Okay. If you look carefully, all these three data sets are identical. So only the way the boundary was established, the technique, okay, that is different. All right. So let's move on. Now the question is, are most machine learning problems based on supervised learning? Is that the case? And also give examples. Well, that is true. That is true that supervised learning does dominates in machine learning. Why it happens? There are a number of reasons for it, which are discussed here. So number one is the abundance of the labeled data, like finance, healthcare, e-commerce, social media. There's lots and lots of labeled data. So labeled data is there, so it's easy. Supervised learning problems have well-defined goals. Predict a specific output, class label, or numerical value based on the input data. So since because this clarity, they are easy to implement, easy to evaluate, and easy to optimize also. Then the techniques and tools are mature. There are decision trees, there are SVMs, okay. Then there are neural networks, then there are libraries, s- 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 TensorFlow, PyTorch, and so on for supervised tasks. And then there are state-of-the-art performance in many real-world applications. So it is well established. Okay. Then these are some of the applications. All right, these are some of the applications of supervised learning. Image classification. So what is image classification? We have covered this before. So label the images based on the visual content, even identifying objects or animals or scenes, right? And of course, there is the ImageNet model which we discussed recently. And these models can recognize and categorize the images with high accuracy, okay, such as the application in medical imaging, security, autonomous vehicles, and so on. Then is spam detection. We need to classify the emails as like junk or spam or ham, which is useful mail. So how it happens? It works with keywords, sender address, frequency patterns, and then many other things. And then the filtering rules are created. So of course, it results in email safety, and user experience is also better. Why? Because junk mails are filtered out. Sentiment analysis, that is usually, this is probably a solved problem. So there can be the sentiment can be in a tweet or in reviews, could be positive or negative or neutral, or it could be surprising and so on. So training is done on annotated data sets, and the model usually can detect the opinions, the emotions, and so on. Speech recognition, it works fine. Predictive maintenance is very interesting. So we have supervised learning sensor data, and it predicts the equipment failures before they occur. So the cost of a problem happening, something that is less than fixing the problem. So it identifies the warning signs by different using of different sensors. So since it's predictive, so it reduces downtime, improves safety, and so on. But remember one thing, which is the however, okay, and that however is important. What is that however? Unsupervised, self-supervised reinforcement learning techniques are getting popular, and for which domains, obviously, where labeled data is scarce and it's expensive or it's not very clear, okay, and of course, then these techniques have become very popular. So let me show you a diagram also at the bottom. So let me first clear this. All right. So this diagram basically shows that we have this instance gathering, we have email data set, and then we perform the training and by dividing into training set and the testing set. So 80/20. And then of course, based upon this, we can divide the SAM from the ham. Spam from the ham. So we are at the question 9. What is multitask learning and how does it works? So some people call it multitasking. It has nothing to do with multitasking. It's multitask. Okay. So of course it's a machine learning technique. Now the novelty here is that instead of having multiple models for multiple tasks, there is a single model. But the catch is that it is the tasks have to be related. So single model, but trained to perform multiple related tasks simultaneously. That's it, right? So what is the goal? The goal is to improve generalization. That's one goal. And another goal is to improve efficiency. And how that efficiency is improved because it kind of capitalizes or leverages on what is common, okay, and what is different across these tasks. So that is multitask learning. So let's go into some details. I'll also share a diagram with you. So shared representations. What is meant by shared representations over here? So these are the common features. Okay, common features which are learned across multiple tasks. Okay, in a neural network. And when does it happens? It happens in the early layers, close to the input. Okay. So what these layers do is that they capture the general patterns, right, from the input data. So how it helps that it enables the knowledge transfer, right, and of course it improves efficiency also, and it improves the performance also, okay, and it improves the it contributes to the transfer learning settings also. So these are the shared representations, right? Let me show you the picture, the diagram, so that it might become all right. So right, so this is these are the different tasks, task ABC, and I'll share with you what is meant by the hard parameters and what is meant by the soft parameters. But you can see that there are different layers, right? And for the hard parameter, they are being shared, okay? So all the hard parameters are being shared, right, for these tasks ABC. And then we can see that for task A there are certain parameters which are shared across those tasks also. So there are two modes, so to say. So let's now go to the bullets. Go back to the bullets. Okay. All right. So we've spoken about the shared representation, and now we speak about the task specific outputs. So what are task specific outputs? They are the dedicated layers or the branches, okay, which are specific to the multitask model, and they handle individual tasks. Okay. So there can be many examples also, and the example could be speech recognition and speaker identification, right? So that could be task specific output, right? So we can see that the early layers may be shared, and these basically specialize in producing certain results, and which are tailored for each task. Yes, because they're specialized, and they ensure accuracy and relevance also. Okay, so those are the task specific outputs. So what is joint optimization? Now, in joint optimization, okay, involves training a model on multiple tasks or objectives simultaneously, and how it is done by minimizing a combined loss function, right? Because you need to optimize, right? So you need to minimize the loss. So what is the objective? That this technique helps the model do some better generalization, learn generalized features, okay, while it is doing a balancing job. And what is that balancing? Balancing the task performance and encouraging the synergy, and at the same time trying to reduce overfitting. And that overfitting, remember, is uh, for any single tasks, for any single task, because by definition there are multiple tasks. Hard and soft parameters, this is what I showed you in the diagram. So the hard parameters are the model weights, okay, uh, which are of course which are shared strictly across all the tasks. That was the single column, which I'll show you again also. And the soft parameters allow task specific adaptation, and which are like across the loosely connected components. So in multitask learning, we are using both, okay, and the objective is to balance the generalization and the flexibility. How? Hard sharing encourages common learning, while soft sharing preserves task specific things, which are called as nuances, so to say. So you see that, let me clear this. So these are the hard or the task specific, shared strictly across the tasks. These ones, okay. And the ones over here, they are the soft parameters, loosely connected components, and we use their combination, right? So then there's one thing very interesting, which is transfer learning. Transfer learning is used a lot in is being used a lot right now. So this is basically about knowledge reuse and of course other things also. So basically what we do is that we let me show you a picture also, okay? So then it will become clear. All right, so let's look at this picture. So this is traditional machine learning. This is transfer learning. So in traditional machine learning, we have isolated single task learning. Okay, there is no retention of knowledge. There is no accumulation of knowledge. Okay, there is no past considerations. So you have data set one, learning system one, task one. Data set two, learning system two, task two. That is the traditional approach. In transfer learning, so what you learn new task that is dependent upon the previous task. So this is data set one, learning task one, and you get the knowledge, and then you use this knowledge and data set two and do the learning system two. So for example, uh, I actually when I was teaching that course in natural language processing, so we were developing a model for tagging different keywords, because the keywords in the healthcare system are different from the keywords in the legal system and so on. So what I told the students which they did was that they used a model which was trained on English grammar, and that English grammar model, okay, data set English grammar model, that's the knowledge, and that knowledge was then used to then that knowledge was augmented by the healthcare data set. That was transfer learning, classical case of transfer learning. I believe you understand. Okay, so let's go to the bullets, right? So knowledge reuse, it capitalizes, it leverages on the knowledge which has been gained from the previous task and use it to improve another task. So what is the objective? It reduces the training time, it reduces the training effort, and it also reduces the energy bill also. And of course, data needs to be reused, okay, and those features are reused, okay, and those representations are also reused. That is one thing. Then is source and target. What is meant by source and target? So we have a source domain where the model is pre-trained, and a target domain where the model is adapted. So I gave you the example of English grammar, then using for the healthcare, using is for the legal and supportive services, using it for some other application, engineering and whatever. So with transfer effectiveness, okay, of course that also depends upon the similarity of the tasks also. Then are the pre-trained models. Pre-trained models trained on large data sets. There are these such models are available in Python, because we use Python in that course. That provide a strong starting point. That provide a strong initialization. Why? Because that has the already captured the general features, and those general features can be fine tuned, can be augmented for specific new tasks. Okay. All right. So, all right. Then is the fine tuning. So what do we do in fine tuning? That do kind of adjustment on the pre-trained model, the weights of those pre-trained models using the target data, and try to do a balance. Okay. And that balance is retaining the previous knowledge and adapting to the new tasks nuances. So that previous knowledge was English grammar, and the new task nuances are related to the healthcare profession, for say for example. And finally is the domain adaptation. So this basically addresses the differences between the source and the target. Source was English grammar, target is healthcare, and that enables the models to maintain the performance across both prior to training and after training, across varied environments or the shifts in the data. Okay, so that your model basically adapts to the new domain. Okay, so that's all for this topic. Thank you very much.